Hey guys, Dr. Urban here. I'm going to go over two short things that will finish up our Chapter 7 videos. I've gone over some basics just to make sure that we're all on the same page and you have, some ideas of examples and things like that. The basics of angular motion. And so definitely go watch the videos that are 1, 2, and 3, talking about those basics and getting us to the kinematics. Well, the other thing we need to talk about that's in Chapter 7 is what actually causes the angular movement, right? So if we have like a box here, right, and it's on something, or have something on something, right, and we apply some kind of force here, this object might move this way, right? So we might get some kind of linear velocity. We might even, when we apply that force, we might start it from rest and we're going to end up having it accelerate. So we might get an acceleration out of that. And we know that Newton's second law there is force equals mass times acceleration. Or a better way to look at it is that acceleration equals, acceleration is directly proportional to force and inversely proportional to the mass. And this is the information you're going to find in chapters 4 and 5, my Newton's laws chapters. And so I'll write in L2 there, Newton's second law. Now we know what's happening, and so this is all like chapter 4 and 5 information. But when we get to chapter 7, we're talking about angular motion or rotational motion. So how does this fit in with this whole Newton's second law phenomenon? I've got something, and actually instead of having it slide, it's going to rotate about some kind of center. Maybe I have a seesaw type object, okay? And there's maybe a force here and a force here that's going to cause that. But what would cause this to rotate? Maybe there'll be a force applied at some distance away. Here, the force, or maybe someone sitting there, maybe it's there's a, I don't know, a little person on your seesaw there, and their weight is causing that downward force vector, and you're pushing on this side or whatever, but that force is at some distance away. That's what causes rotation. And again, maybe the other one we could look at that I've put on the board is some kind of bar like this, where I have some force that's applied here at some distance out, r. So what we're figuring out is that in the chapter 4 and 5 type of motion, if we want to have something move in the x direction, forward or back or up and down, we're going to apply a force of some sort that causes it to slide or move in that way. When we're talking about angular motion and we want something to rotate, we're going to have to apply a force out at some displacement from wherever the pivot is. Here, the pivot is here. Center of a circle, the pivot's here. Here, if this were something maybe attached to a wall, that's where our pivot's going to be. So I'm not really working with forces, just a force. What I'm working with is torque. And that's going to be the perpendicular component of the force applied out at some displacement. Okay, so again, if I were to take this bar, these are like the door handles in the classroom, and I apply a force maybe downward, let's expand this idea. What if I apply a force like there or here, or maybe ours in the classroom you can't really lift up on, but I can apply a force at some angle to the door handle and cause it to rotate. But if I were to apply, say, a force straight in on the door handle or straight out on the door handle, this is not going to cause torque. So I need the perpendicular component of the force. The author also writes it as force sine of the angle times the displacement out. So what angle are we talking about? So let's expand this picture. So I have a bar stuck to a wall, like the door handles in our classroom. Okay, here's the pivot. Here is the force applied on an angle. Where is the angle actually? Like where would I calculate it from? Well, you're going to calculate that angle, and it'll usually be shown in the problem, or it'll say blah blah degrees to the radial line. Well, this is the distance out. I'll write it below. So this is the r where F is applied. This is the distance out from where the force is applied to my pivot here. And it looks like this force is applied on this angle from the radial line. In other words, I'm going to get the up and down portion of this force. Okay, that's why we have the sine of the angle. So how would you do these problems? Well, let's set a couple of them up, and then we're going to talk about the last piece we need. I'll fill this in the next video. So let's take this exact example. Okay, so we're going to do 2. So save a little space. So I'm going to put this bar here. Okay, and I'm going to have, say, we'll call this force 1 here, and we're going to call this force 2. And let's see how many markers I have here. So force 1 is out at a distance of R1. That's where force 1 is applied, right there. That's that distance R1. And I'll make it blue, so it's a little easier to follow what I'm doing here. Force 1, we'll make it blue. And force 2, we'll keep it in the pencil lead color, is applied a little bit further out. It's applied at this distance R2 right there, okay? And force 1 is, let's say, what does that look like? That looks like of an angle about maybe 55 degrees, I don't know. So how would I calculate if I wanted to sum my torques, or is this going to spin? Well, let's say in this example, force 1 is 11 newtons and force 2 is 11 newtons, okay? So how would I do this? I'm not gonna solve it out all the way to a number. I'll leave that up to you. But how would I sum these torques? Well, you have to remember, every time from now on at the top of the page, I need to see CCW positive, which means counterclockwise is positive. So as I look at this, I'm going to use my pencil as an example. Force 1 is going to cause the bar to rotate, clockwise. So that's going to be, force 1 is going to cause negative torque. Just make a note about that. Force 2, if it was alone, would cause the bar to rotate counterclockwise. So this one's going to cause positive torque. So I'd say sum my torques, and I would add torque 1 to torque 2. Let's expand that. Torque 1 is force 1 perpendicular component times R1. I'll make my 1s a little easier to read there. Plus force 2 R2. Okay, this is just, no numbers are in here yet. Now I need to remember which one causes positive or negative, so I'm still summing my torques here. Force 1 is going to be 11 newtons. Oh wait, that's going to cause negative torque. So let's put that here. So that would be negative 11 newtons times sine of whatever that angle is, 55, times the distance is, I forgot to tell you guys, let's make this 1 meter, and let's say this is let's make it 1.1 meters, this is 1.2 meters, so I'd multiply this by 1.1 meters. And then force 2 is going to cause it to go counterclockwise, so let's say that's 11 newtons, and it's applied at 1.2 meters out. Okay. So what is the sum of those torques? I will put this in the caption of the video.